Everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore, and today we are going to discuss about second order systems in time response analysis. In previous video, we have discussed about time domain specifications and we have discussed an example, and in that example we are fetching time domain specifications and the elements of time domain specifications, and here we are moving into second order systems. See, consider the following block diagram of the closed loop control system. Here the open loop transfer function is omega n square by s multiplied with s plus 2 del omega n. It is connected with an unity negative feedback. The system is called as second order system because the order is 2. See here, C of s by R of s it is equal to G of s by 1 plus G of s multiplied with H of s. Here H of s is equal to 1, so the formula is G of s by 1 plus G of s only. And it is also written as omega n square by s plus 2 del omega n s plus omega n square. Here R of s is your input, C of s is your output, and also we have summing point plus minus, and the transfer function of the system is omega n square by s multiplied with s plus 2 del omega n. And finally we will get omega n square by s square plus 2 del omega n s plus omega n square as the output of C of s by R of s. Okay. Depending on the value of damping ratio, second order system can be classified into 4 main parts. First one is underdamped system, second one underdamped system for del equal to 0, and second one is underdamped system for the values of del between 0 to 1, and critically damped system del equal to 1, and overdamped system del is greater than 1. Here the characteristic equation is s square plus 2 del omega n s plus omega n square equal to 0. Here the del value is varied depending on the system's damping ratio. Del might be 0 or 0 to 1 or equal to 1 or greater than 1. Based on the system's damping ratio, it might be varied. Okay. Here the roots of characteristic equation is given by s equal to minus del omega n plus or minus omega n multiplied with root of del square minus 1. Here the roots are imaginary when del equal to 0. Here the roots are real and equal when del equal to 1. The roots are real and unequal when del greater than 1. The roots are complex conjugate when del equal to 0 to 1. See the difference. We have different del values, del equal to 0, equal to 1, greater than 1, 0 to 1. Here the roots are varied depending on the del value. The roots might be imaginary or real, real with equal or real with unequal or complex conjugate based on the del values. Okay. Here, for an underdamped system, the step response of underdamped second order system is C of s by R of s it is equal to G of s by 1 plus G of s into H of s. It is equal to omega n square by a square plus 2 del omega n s plus omega n square. When del equal to 0, the value of C of s by R of s it is equal to omega n square by a square plus omega n square. Time response of the system for unit step input is C of t equal to 1 minus cos omega n t here. See the diagram. Here we have CSS of t and steady state, and here del equal to 0. For del equal to 0, the value is 1 minus cos omega n t, and it is represented in terms of signals. Okay. For an underdamped system, the step response of underdamped second order system is given by C of s by R of s it is equal to G of s by 1 plus G of s into H of s it is equal to omega n square by a square plus 2 del omega n s plus omega n square. We know that when del value lies between 0 to 1, the response of the system of unit step input is C of s by R of s it is equal to A by S plus BS plus C divide by s square plus 2 del omega n s plus omega n square. It is all derivations, so we have to consider this. The final output is C of t is equal to 1 minus e power minus del omega n t divided by root of 1 minus del square multiplied with sine omega dt plus theta. See the output oscillations are, how it is represented over here. Here for unit step input, the output of system is C of t is equal to 1 minus e power minus del omega n t divided by root of 1 minus del square multiplied with sine omega dt plus theta. For a critically damped system, we consider the step response of underdamped second order system C of s by R of s, it is equal to G of s by 1 plus G of s into H of s, it is equal to omega n square by s square plus 2 del omega ns plus omega n square. Here in this formula, del equal to 1 means the response of system for unit step input is C of s by R of s, it is equal to omega n square by s square plus 2 omega n s plus omega n square, because del equal to 1. Here C of t value is 1 minus e power minus omega n t minus omega n t e power minus omega n t. Here the value of C of s, it is equal to omega n square by s multiplied with s plus omega n the whole square, which is equal to a by s plus b by s plus omega n plus c by s plus omega n the whole square. Okay, see here the second order response, how it is denoted, and see here already we have seen the oscillations and signals of underdamped, critically damped, overdamped systems. Here the collection of second order response is given. First we have in the x-axis we have omega t, and y-axis we have step response, and the green lines are representing underdamped system del equal to 0, and undamped system del equal to 0, and underdamped is this blue color del equal to 0.5, and critically damped del equal to 1, it is in red color, and in pink color it is overdamped del equal to 1.5. That's all about the second order systems. Thank you.